Hey everybody, this is Mr. Beckstrom, and today I want to go over an example from section 7C, and it says, suppose you play a coin toss game in which you win $1 if a heads appears, and you lose $1 if tails appears. In the first 100 coin tosses, heads come up 36 times, and tails come up 64 times, and they want us to answer these questions here. All right, so let's go ahead and talk about this. The first question is, what percentage of the time has heads come up in the first 100 coin tosses? Well, to calculate a percentage, you just take the number of times it occurred, or the over, this is 36 times, over the total number of occurrences or events, I guess in this case observations, that would be 100. And you're going to get 0.36, which convert that to a percentage, and that is 36%. So we're going to put 36% of the time we actually got a heads. That is not very good because on average it's 50%. So we are definitely unlucky in this game so far. Now it says, what is your net gain or loss at this point? Select the correct choice and fill in the blanks. Well, we're just going to select the correct choice here. So how much did we win or lose? Well, we won 36% of the time. So if I do 0.36 times, or 36% of the time we won, which we actually, we actually won 36 times. So 36 times we won $1, right? And 64 times we lost $1. So we won 36 and we lost 64. So our net is 36 minus 64, which is $28 that we lost. So we lost $28. So lost $28. 28 bucks at this point here. All right, and let's go on to B here. It says, suppose you toss the coin 200 more times, a total of 300 tosses. At this point, heads has come up to 39%, so it was at 36% before, but now our total is 39%. Is this change in the percentage of heads consistent with the law of large numbers? Explain. All right, so let's talk a little bit about the law of large numbers. The law of large numbers basically tells us that if we just keep tossing a coin or doing some event a huge number of times, that we're going to approach the probability of it actually happening. So for example, if we have a 50% chance to win $1, the more times we flip it, the closer that we're going to get to winning 50% of the time. So if you were to toss a coin 1,000,000 times, that percentage of you winning should be very, very close to 50%. And it just goes up. It gets closer and closer to that percentage the more number of times that you complete that event. So in this case, we were at 36% and we tossed it a couple hundred more times and we got a little closer to 50%. So that is exactly what the law of large numbers tells us, that the more times we flip it, the closer that we should get to that percentage, that actual probability percentage. All right, so the change is consistent with the law of large numbers because the percentage is low the first 100 trials. It has to be higher. No, the percentage actually stays the same. It's still a 50% chance to win every time we flip it. So this one is not correct. So let's look at the other consistent one. The change is consistent with the law of large numbers because as the number of trials increases, the proportion should go closer to 50%. So that is exactly what we just said here. All right, for number C, or letter C, how many heads would you need in the next 100 tosses in order to break even after 400? So we've tossed it 300 times. So let's go over here. So we've already tossed it 300 times, and we have won 39% of the time. So I'm just going to multiply that by 0.39, and that'll tell me how many actual times that I have won. So I've won 117 times. Now it says how many heads would you need in the next 100 tosses in order to break even? All right, so if we were to break even after 400 tosses, that means we would have needed to have flipped heads 200 times, right? Because that would be breaking even. Since we win $1 when we flip a heads and we lose $1 when we flip a tails, after 400 times, we would need to have won 200 times. But so far, we've only won 117 times. So in order to win 200, we are going to have to win 83 more times out of the next 100 tosses, right? Because we need to get that win count up to 200. So that's just the difference between 200 and the 117 that we've already flipped. And so that would be 83. So how many heads would you need to flip? So 83 heads. Oops. 83 heads out of man, I can't write today. 100. All right. And is this likely to occur? Are you likely to flip 83 heads out of 100 coins? Well, we know that the average is going to be 50. So 83 heads would be very unlikely because the probability to flip a heads is still 50%. So you would have to win 83% of the time in order to do this. So no, this would be very unlikely. And suppose that still behind after 400 tosses, you decide to keep playing because you are due for a winning streak. Explain how this belief would illustrate the gambler's fallacy. So the gambler's fallacy basically says that if you have a certain probability in order to do something, and that probability doesn't change, you're still gonna be on average, doing that when you do that event a huge number of times. So there would be D here, right? This illustrates the gambler's fallacy because the number of heads cannot be. Oh, wait. Oops. Eventually, there would be a winning streak because the number of heads cannot be under. Yes, I'm sorry, B right here, right? This illustrates the gambler's fallacy because the probability of getting heads is always 0.5. It's always 50%. All right, well, that's it. I hope this helped. If you have any questions, please let me know. Have a great week. Thanks.